Hello, my dear students. Welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the orbital concept of the covalent bond formation. But before doing that, let's study about the orbitals. In the chapter of atomic structure, we have done the quantum numbers, and there I have told you that the main principal shell will have subshells, and in subshells we will have the orbitals, and at orbitals we will have the spin of the electrons. Now, the subshells are of four types: the S, P, D, and the F, and these subshells will have the orbitals. The orbital of S subshell will be spherical in shape, whereas that of P, D, and F will be in dumbbell shape. However, that dumbbell will have a different directional constraints in XY and the Z axis for the P, D, and the F subshells. Now let's start. In the main energy shell, we are having subshells, and that subshells are S subshell, P subshell, D subshell, and the F subshell. Now, the S subshell will have only one orbital. The P subshell will have three orbitals. The D subshell will have five orbitals. And the F subshell will have seven orbitals. Now, let's talk about the shapes of the different orbitals. The orbital of S subshell, that means S orbitals, will be spherical in shape. Will be spherical in shape. That is, if this is the nucleus, then the S subshell will be like this in the sphere model. Now, let's talk about the P subshell, D subshell, and the F subshell. The orbitals of these three subshells will be in dumbbell shape. Now, as this is the nucleus, so dumbbell shape will be like this. So, what is orbital? The orbital is a three-dimensional region around the nucleus where probability of finding electron is maximum. Now, let's apply the concept of orbitals in the formation of covalent bond. Now, but before doing that, let's talk about the spin of the electrons. Now, in the orbital, we have maximum of two electrons. I am writing one orbital will have maximum of only two electrons. Max of only two electrons. Now, as the electrons are negatively charged, that means then the two electrons in the same orbital will have the interelectronic repulsions. So to minimize that repulsion, the two electrons will be of opposite spin. So max of only two electrons, but with opposite spin. That means if in an orbital the one electron is like this and the spin is plus 1 by 2, then the other electron will be like inverted, that is the spin of minus 1 by 2. So the two electrons in an orbital will exist only with the opposite spins to minimize the repulsive forces. Sorry. Now, let's apply this concept in the formation of covalent bond. I am taking an example of hydrogen molecule. Let's talk about the hydrogen molecule. It is H2. Now, here's my first hydrogen, there's my second hydrogen. The hydrogen, now we have to talk about the electronic configuration in terms of subshell. So the electronic configuration of hydrogen is actually 1s1. So the another hydrogen will also will be 1s1. Now, this is the nucleus of first hydrogen. Here the electron is present in the s subshell. So the orbital of s subshell will be spherical in shape. So this is the s orbital of the first hydrogen. This is the nucleus, and this is the spherical orbital of the second hydrogen. Now, what will happen? As both of the orbitals are having one electron each, that means here electron is present like this with the plus half spin. So the another hydrogen must have electron with the opposite spin. This is the minus half spin. Now, S orbital can accommodate maximum of 2 electron, but in hydrogen there is a presence of only 1 electron. So the hydrogen will try to have 2 electrons in the s orbital to attain stable noble gas configuration of helium, which is 1s2. So in the covalent bond formation and according to the orbital concept, what's going to happen? These two orbitals will approach to each other and there will be the overlapping of the atomic orbitals. I'm drawing that. So this is the nucleus of first hydrogen, and that's the 1s of the first hydrogen with the electron of plus 1/2 spin. Now there will be the overlapping of the atomic orbital. So this is the nucleus of the second hydrogen, and this is the 1s of the second hydrogen, and there is the overlapping of the atomic orbitals, the 1s of the first hydrogen with the 1s of the second hydrogen. So this is the overlapping of the atomic orbital, and both the electron with the opposite spin will come in the overlapped zone. So this is actually the covalent bond formation. So I'm repeating it again, that the 1s orbital of the first hydrogen will overlap with the 1s orbital of the second hydrogen. So when the overlapping will take place, when both the orbitals will be having one electron each but with the opposite spin. Now after the overlapping, both the electron of opposite spin are in the overlapped zone. That is the base for the formation of attractive forces, or we can say the formation of the covalent bond. So now let's talk about the overlapping between s and the p orbital. So this is the overlapping of s and the s orbital. Let me write this thing for you. This is the overlapping of s and s orbital. Now let me take an example of overlapping of s and the p orbital. Now let's take an example of, I'm writing overlapping of s and p orbital. For that I'm taking an example of hydrogen chloride. Now I'm writing hydrogen over here and chlorine over here. Now, what's the electronic configuration of hydrogen in terms of subshells? It's 1s1. What's the electronic configuration of chlorine in terms of subshells? It's 1s2, 2s2, 2p6, 3s2 and 3p5. Now, in case of chlorine, focus on the valence shell, that's 3p, the valence subshell 3p. Now in 3p we are having 3 orbitals. and it's like this. This is 3px, this is 3py, and this is 3pz. Now the electronic configuration is 3p5, so we have to follow the Hund's rule. That is, we have to give one electron each to the each orbital, then pairing will start. So the first electron over here, second over here, third over here, we have to fill 5 electrons. So fourth over here, fifth over here. So finally at the last we got the 3pz, which needs one more electron, to get paired. So 3pz will be the orbital which will overlap with the 1s orbital of the hydrogen. Now I'm writing again over here. So hydrogen, this is the nucleus of the hydrogen. The S subshell is spherical in shape, right? So here the S subshell is having an S orbital is having an electron with a spin of plus 1 by 2. Now let's talk about the 3pz. Now it's in p orbital, which is spherical, which is dumbbell in shape. So this is the dumbbell shaped atomic orbital of the chlorine, and it's 3pz. This is 1s. This is 1s1, this is 3pz1, because 3pz is having only one electron. Now 3pz must have electron with the spin of minus 1 by 2, only then the overlapping will take place between the two atomic orbitals. So these two atomic orbitals, hydrogen is 1s1, it needs one electron to complete its 2 electron in s orbital, whereas 3pz needs also 1 electron to complete 2 electrons in 3pz orbital. So these two orbitals will overlap with each other, and here the s orbital of hydrogen is overlapping with the pz orbital of the chlorine. So overlapping will be like, this is the nucleus of hydrogen, this is the S subshell with the electron having a spin of plus 1 by 2. On the other hand, this is the nucleus of chlorine, and this is the 3pz, and that's the overlapped zone in which the electron of chlorine will also come and pair will take place, and pair formation will take place. So both the orbitals, that's 1s and the 3pz, got 2 electrons each. So here the formation of covalent bond has took place. So after the formation of covalent bond, the 2 electrons with opposite spin, that is plus 1 by 2 and minus 1 by 2, are in the overlapped zone of the s orbital and the p orbital. So that's the example for overlapping of s and the p orbital. Now let's talk about the overlapping of p and the p orbital. Now I'm taking an example of overlapping of p and p orbital. For this overlapping, let's take an example of chlorine molecule. I'm taking an example of chlorine molecule. It's Cl2. Now I'm writing chlorine over here, chlorine over here. So the configuration for both the chlorine will be 1s2, 2s2, 2p6, 3s2, and a 3p5. Here valence subshell is 3p, which is having 5 electrons, and it needs one more electron to get completed as 3p6 and to attain the stable noble gas configuration of argon. Now for another chlorine, it will be again 1s2, 2s2, 2p6, 3s2, and the 3p5. For both the cases, we have to draw the orbital diagram. As p is having 3 orbitals, that's px, py and the pz. It's actually 3px, 3py and the 3pz. Now here we have to fill 5 electrons. The 5 electrons. For that we have to follow the Hund's rule. That means all orbitals will get 1 electron each. After that the pairing will start. So it's 1, 2, 3, 4 and the 5. Now let's talk about the another 3p of the another chlorine. It's again 3p. So it's 3 orbitals. It's 3px, is 3py and is 3pz. Here again we have to fill 5 electrons. So it's 1, it's 2, it's 3, it's 4 and it's 5. So here in both the cases, what's gonna happen? Here this 3pz will going to be overlapped with this 3pz. That is to share the electrons present in 3pz with each other to complete the octet of both the chlorines and to attain the stable noble gas configuration of argon of 3s to 3p6. So let's draw the shape of the 3pz orbital. This is the nucleus of the first chlorine and this is 3pz. The dumbbell shape is 3pz with dumbbell shape and it is having an electron with a spin of +1/2. I'm saying it again, overlapping of atomic orbital will take place only when the overlapping orbitals are having electrons with opposite spin. Only then overlapping will take place. Now let's talk about the 3pz orbital of the another chlorine. This is the nucleus. This is the 3pz, the dumbbell shape of the second chlorine, and here is having an electron with a spin of -1/2, the opposite spin. Now both the orbitals will move closer to each other for overlapping and it's gonna form a, this is the nucleus. This is the first dumbbell, the 3pz, and this is the second dumbbell, but before that this is the electron of 3pz of the first chlorine. Now the overlapping will now the overlapping will take place between the 3pz and the 3pz. Now overlapping will take place. So this is the overlapping between the 3pz and the 3pz, or we can say that overlapping between the p orbital and the p orbital, and this is the electron with a spin of -1/2. Now both the electrons with the opposite spin have come under the overlapped zone of the 2p orbital. So that's the covalent bond formation between the p orbital and the p orbital. So I hope you all understood today's lecture, but one point I'm repeating it again so that you can have the clarity that atomic orbitals will overlap only when both are having 1 electron each but with opposite spin. Only then it will take place. So here we have done 3 examples. The example of hydrogen molecule in which the overlapping of SS orbital have taken place. The molecule of HCl in which the overlapping of s orbital of hydrogen and the p orbital of chlorine has taken place. And the third one is the overlapping of p and the p orbital. Here we have taken the chlorine molecule in which the overlapping of 3pz of first chlorine and the 3pz of second chlorine have taken place. When the overlapping will take place, the electrons of both the orbitals but with opposite spin will come in the overlapped region, and this is the covalent bond in reality. So that's all for today. I hope you all understood today the orbital concept of the covalent bond formation, which is going to help you a lot in the further topics of hybridization, valence bond theory, Vesper theory, the molecular orbital theory. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then he/she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.